Now, the 1981 Nobel Prize in Physics was basically for advances in the form in different areas of atomic spectroscopy, which means you can measure things down at the one atom level, or multiple atom level, but down at that level. And it's really interesting stuff. Now, half the prize was shared by a professor named Nicolaas Bloembergen and Arthur Schawlow. And what they did was they developed a bunch of things when it came to laser spectroscopy. And now the other half of the prize went to Kai Seigbahn. And what he did was he developed a lot of high resolution electron spectroscopy. But at the end of the video, what you're going to see is that everything along here, they were just trying to measure what went on at inside atoms, or what went on in different energy levels of atoms, or look at materials and see what the composition is down at the atomic level, all of which becomes very important, not only in science labs, but in your day-to-day life. And has certainly impacted you at some point in your life, whether or not you realize it. And it certainly has shaped the world around us in ways that may not necessarily be all that obvious on the surface. So let's take a little bit of a dive and kind of start looking at it, and then we'll get to why I feel it's important. Now, quantum physics tells us that electrons inside atoms and molecules have very well-defined and very specific energy levels based on which atom or molecule you're talking about. Now, Einstein's Nobel Prize-winning project that he published in 1905 and won the prize for in 1921 was called the photoelectric effect. And it says that a light particle, which is known as a photon, can actually liberate or knock an electron off of an atom if it has sufficient energy, which it's all over. I mean, the photoelectric effect describes this very plainly. And in the 1950s, Kai Seigbahn developed an apparatus and a bunch of methods of achieving highly accurate measurements of those energy levels in atoms all over the periodic table by irradiating them with photons of very specific frequencies of light and measuring the energy of the electrons emitted by that photoelectric effect interaction in between the two. So what he was doing was using Einstein's work to say, okay, great, let's go use that work to understand these atoms a lot better. And what he did. And basically, he used one Nobel Prize winning project to build apparatus and do laboratory experiments to win another one. So basically, the Einstein effect. Einstein's still being felt in physics, the 55 years after he did the project. They're still being felt all over the physics community today. There's people that would love to be able to figure out how Einstein made a mistake someplace, which has never really been found. But now, what was the other half of this prize? What do the other guys do? Because that's using electrons to do this stuff in light. Now, what about the other guys? Let's go take a look. Now, Bloembergen and Schawlow. Schawlow, by the way, wrote a really good book on microwave spectroscopy that I've got a copy around here somewhere. It's great stuff. But anyway, as explained by quantum physics, there are transitions between energy levels, and light of specific frequencies is either emitted or absorbed by those atoms and molecules when those transitions take place. So it goes from a not excited state to an excited state, and there's a bunch of excited states, and light comes out when it goes either into or out of that state. And it's very well known now what those wavelengths light are. It's well known because of work like this. So in the 1960s, Bloemberg used laser light to determine the energy levels with great precision. Basically, he used 3 laser beams to go into a sample of material, usually in gaseous state. It can be in solid, but in gaseous state in this case. And a 4th laser beam would be created, and a larger part of the spectrum could be investigated through this sort of interaction and this emission. And that allowed him to look at the emission side of the spectrum. Now, some atoms can be looked at the other way, where you see what light is absorbed. So there's another side of this called absorption spectrum, which was what Schawlow did in the 1960s. And he used that phenomena to basically eliminate the Doppler effect of what went on when looking at those transitions. So he used absorption and elimination of the Doppler effect to get to, again, a very highly specific precise measurement of those energy levels inside atoms or molecules. And these were techniques that just hadn't been done up to that point. And you may look at it like low-hanging fruit, because it's one of the comments I get on the channel all the time is, well, it was all low-hanging fruit. Well, Okay, it might look that way looking backwards, but if you're doing it for the first time, I bet you it didn't look like low-hanging fruit to them, right? So maybe it looks that way, 60 something years later, but it was not that way in the lab. And I've been around Nobel Prize winners. I've met a bunch of them, and you look at it and go, well, that's so simple. And they're like, yeah, now, but it wasn't all that obvious at first, right? So now I promise that this stuff is actually important to your life. And you're probably saying, yeah, but so what? This is just a bunch of nerds in a lab. Let's look at why it's actually important and really does matter to you and has shaped the world around us. I promised at the beginning of the video to tell you why you give a crap, and you really do give a crap. This is not just some nerds in a lab trying to do measurements. So it is certainly used for chemical analysis in labs, material science analysis, environmental science, astrophysics. It's certainly used for that kind of stuff. But it's also used, all of these atomic spectroscopy, whether it's electron or laser light or however, absorption, emission spectroscopy, it's used in forensic science and crime scenes all the time. So it can actually help people solve crimes, which is why certain types of crimes are almost never heard of anymore. At least not in the same they got away with it frame that they used to be. Now, medical diagnoses, and that's not to say crime rates aren't bad. They are, but there's certain things that forensic scientists can uncover to find out who did something that weren't available 40 years ago. Now, also medical diagnoses. So you can use these things to look at trace elements in a body or in a tissue sample, and say what's really wrong with somebody. And using this type of work to figure out what's wrong is common practice. It's used in art conservation. It's used in looking at impurities. So when you start talking about, hey, what's wrong with the groundwater around here? What's wrong with different things? You're using these types of sometimes you're using these types of spectroscopic measurements to determine how things are impacting our daily lives, and especially when it comes to medical use and medication. It's very important stuff. So it may sound like a bunch of nerds off in the lab, and yeah, it's not something, I'm going to go run off in my garage and do atomic spectroscopy, but it does have impact in our daily lives, and it's not just something that's just for university, ivory tower kind of people. It's really cool stuff. So we will see you on the 1982 prize, which I think is also kind of a fun one. And these are getting more interesting as we get into more modern ones. And at the end of all this, I'm going to do sort of a timeline of what all we've learned from 1901 till now, which I think has some huge stuff in it. And I think sometimes in the modern world, we look at science and go, well, we've known that forever. Well, not really. Some of it, you say we've known forever. We've only known since like the 1960s or 70s, right? So it's not that old. But stay tuned. Don't forget to click like and subscribe. We will see you on the next one.